speaker today is Perry Jones, and it's titled, as you know, Assessing the Influence of Natural Copper-Nickel Bedrocks on Water Quality. Perry Jones is a hydrologist. He's with the U.S. Geologic Service, Minnesota Water Sciences Center, where he's been working for, 17 years, I think? 19 years. 19 years.
19.
He's older than he looks.
Yeah.
He received his BS degree from the State University of New York in Portland and an MS degree in geology also from the University of Minnesota. He's previously worked for 7 years at the U.S. Bureau of Mines. You are older than you look. Besides his research into baseline characterization of potential mining areas in northern Minnesota, Perry's assessing groundwater and surface water interactions in the White Bear Lake and other Twin Cities metro lakes, which, by the way, is a big deal down in the Twin Cities. Without further ado, please welcome Perry Jones.
Thank you, Jan. I'm going to talk. If you can't hear me, please let me know. I'm going to make this as lax as possible, so if you have questions in the presentation, please raise your hand and let me know, or speak up. So thank you, Jan, for your introduction. I just want to recognize that this is a 3-year study that we got funded through the Legislative Citizens Committee for Minnesota Resources. And it's a cooperative study between a group that's with the USGS, Laura Woodruff is the lead geologist in it, Robert Seal and the Tech or others, and there's others from the USGS working on this project. But we're also working with the University of Minnesota Duluth Natural Resources Research Institute, Steve Hump. And also, we have a glacial geologist who's working with us, Terry Jennings from the Minnesota Department of Natural Resources. And it's a 3-year study, and it's really to characterize some of the regional water quality and how it may be associated with some of the bedrock issues. And the study actually started in 2013, but before that, we've done some work in Minnesota dealing with some watersheds that are where potential mining could be occurring. And in 2011, we started with the St. Louis River and looked at stream sediment chemistry as well as stream flow and also water quality, and working with the Great Lakes Indian Fish and Wildlife Commission as well as the Fond du Lac Reservation and with Environmental Protection Agency. And in 2002, the USGS Midwest area had some funds available to do some additional work, and they asked us to characterize work in 3 watersheds, Gilson Creek, Keeley, and the St. Louis Rivers. And these are all watersheds. I'll show you a map where they're located. But they're all watersheds which are along the basal part of the Duluth complex. And that's where a lot of the proposed nickel copper mines or mining is proposed for. But there's other minerals, and I'll show you those areas too, at potential sites. So we got some money to do some in 2012, water quality and street bed sampling, additional work in those 3 watersheds. And then we came through with the money of the most recent study, which we'll talk more in depth, dealing with looking at the bedrock and the soil chemistry, as well as the additional work with water quality and stream flow. And then finally, EPA has given us some additional money to do further characterization, looking at other specific issues, looking at things like stable isotope chemistry to help us get a better understanding of the hydrology, and also looking at the amount of dissolved organic carbon, which is really important in understanding how the water chemistry will change over time. So anyways, so we mentioned 3 watersheds. And I'll point this out. Again, we're up in northeastern Minnesota. If we look here, this dotted line here represents the contact between the Duluth complex, which is a bunch of series of igneous rocks that was formed as far as volcanic material. And everything to the east here is part of the Duluth complex. And it's butted up against what is called the Virginia Formation. And if we look at these 2 watersheds, one is Filson Creek. Keeley Creek's located up right adjacent to Filson. And then we're looking at the headwaters, basically the area which is where the Duluth complex is located in the St. Louis River. And why we picked these 3 watersheds is we want to get an idea of what the general water chemistry is, kind of the background chemistry of along that basal part of the loop complex. So we're looking at kind of a band through here, which is kind of the lower part of the loop complex. And so why we pick these three watersheds is because they kind of represent different geologies within those watersheds, particularly looking at mineralization. And if we look, Filson Creek is an area which has known nickel, copper, and PGE, or platinum group element metals. And these are important. These are the ones that potentially could be mined in the future for profit. We picked out Healy Creek because there isn't very much known mineralization through that watershed. So we kind of used that as kind of a background. And then we looked at the headwaters of the St. Louis River because there's known iron, titanium, and oxide deposits, which are different mineral deposits through this section. And those are the black dots here. The red areas here indicate where there's been identified nickel, copper deposits. And so we picked those to get kind of a regional perspective of different geologies and to see what the water quality is in those areas and how it might be or may not be related back to the geology. So I mentioned this recent study we started in 2013, and really it's to assess what the influence of the Duluth complex bedrocks likely have on water quality. And so what we've done is focused is to characterize the metal concentrations, but we've also looked at the whole general chemistry of surface water, bedrock, streambed sediments, and soils in the area across that basal part of the Duluth complex. And then the focus is again to determine if the metal concentrations are currently influencing the regional water quality. Do we see a regional pattern associated? And so what's the purpose of this? What are we trying to hopefully to do is we want to establish a current regional pre-mining baseline geochemistry for the different environments, the soils, chemistry, rocks, and the water. And we want to create a data set that's available or tools that can be used to assess the potential impacts of potential mining in those areas on water quality. We're hoping that the outcomes then can be used by the federal, state, and local tribal entities and the mining companies to get a sound public policy with regard to decisions on whether mining to go through or not. So we are here to kind of establish a baseline that data can then be used for decision making. So our study design was, again, to determine the major and trace element contents in bedrock samples, soil samples, and streams within those three watersheds. And then we look at flow rates. We're also monitoring stream flow. We've got stream gauges located in each of the three watersheds. And then try to figure out, looking at the water quality and the stream flow, how much metals are being transported through the systems. And then the final activity is we're constructing conceptual models or ideas of what the hydrology looks like and what's the water quality, current water quality issues associated with the watersheds, with the idea that then we can figure out what are the important parameters that may be needed to be looked at in the watershed. And so our water quality sampling started for this project, 2014. It continues now. In fact, I have a team up there now. They're just finishing up this week sampling. And what they're sampling for is we've got in all three watersheds, we have a total of 21 sampling sites that we collect water samples. And we're collecting samples 4 times a year, last year and this year. And we're looking at trace elements, 18 trace elements, major ions, major chemistry ions, 12. And then we're looking at dissolved organic carbon, which is really important. It's a really important parameter to look at in the water quality because I think it's controlling a lot of the movement of metals. And we also look at the total amount of organic carbon, dissolved and total. And then I mentioned stable isotopes. We typically, as hydrologists, use stable isotopes to figure out what the hydrology is. It's a good parameter to look at for determining what the hydrology is in the system. Yeah.
Your 4 times a year, is that year-round, or is it just ice-free?
It's typically ice-free, but what we try to do is get early and right after snowmelt as soon as we can, our first round sampling. And then we go as late as October, typically. So that's kind of the round. We don't sample in the winter. Now, for our solid media, again, that's the bedrock soils. We're looking at collecting 10 bedrock samples in each of the watersheds, and we've already done that, and greater than 30 soil samples. And we collected the top and the sea horizon. We'll talk about some of the sea horizon soils, and I don't know the classifications for soils, but there are some of the deeper soils. And then we've collected 20 streambed sediment samples, and we divided them up into different fraction sizes to look at the finer components versus the more coarser components in those samples. And with each of these types of samples, we're looking at 44 major and trace elements. And we've also looked at 10 metals in particular that what we've done is looked at the leaching potential for those metals. So we've added a weak leach to those metals, and then see how the concentrations change from what we have from the natural versus through the weak leach analysis. And that gives us an idea of how much of this material may be leached out through the system. And so just to get some pictures and show what the sites look like, these are some photos from Filson and Kiwi Creek. And the properties in the watershed, we've got abundant wetlands, which I'm sure you know, most of you know, through the watersheds. Several lakes, the streams flow through several lakes, and so there's that interaction that occurs. These areas, the glacial cover, the amount of glacial material above the bedrock that was deposited by the glaciers is pretty thin, typically less than 50 feet, but more, in most areas, it's less than 20 feet. And the topography of the area is really controlled by the bedrock. There's a lot of places where the bedrock is actually at the surface and exposed at the surface, and I'll show you some photos of
How do you characterize it as thin? What's thick?
typical thick. Oh, you go down to parts of the state, there's places where you get 300 feet, or it just varies 200, 300 feet sometimes. Yeah. So this is the Filson Creek watershed here, and then here's Keeley. It butts right up against it. And so this is a map showing where we collected water samples as well as soil and bedrock samples. The red dots indicate where we have water samples. And in Filson Creek we have one arm that goes through this way, and then a second trip that comes through, runs through and crosses, and they all fall into the Quishley. Keeley Creek, which is our background site, it just has one stream through here and then a second trip coming in through here, and that pushes into Birch Lake. And so we also installed a stream gauge right here on Keeley Creek, and we've got the DNR actually has a stream gauge on the main channel through here at Spruce Road. But we also installed a gauge on one of the arms of the river, so that we can get a handle on what the flow conditions are in this portion of the river. In particular, because through this, and I'll show a map later, but there's one of the deposits, nickel copper deposits identified, is right in this section right, of the creek, and it's exposed at the surface. So we really wanted to get a good handle of what the chemistry and the hydrology is through that portion of the watershed. Okay, so the headwaters of the St. Louis River, again, we have abundant wetlands. There's minimal bedrock exposure. There's a lot of more thicker deposits of glacial material on top of this. Typically, we see 100 to 150 feet thick of glacial material. And this is sands as well as clays, different types of deposits in those areas. And the topography is really controlled by what the glacial material is, because the bedrock is so depleted in these areas. And what you'll find is where we've got towards the edge of where we're sampling, where the Virginia Formation is pretty obvious. You can see the shales here that are located on there. And then we have plenty of areas where we've had these huge boulder fields of rock. And a lot of these are boulders that were from the Duluth complex that got pushed through by the glaciers and through meltwaters and got deposited through these parts of the river. And in between those areas, you get wide sections, which are typically you get a lot of wild rice and other things growing in the stream. And so here's a map showing our area of where we're sampling in the headwaters. The red dots indicate we have 7 locations where we've got stream water quality samples we're collecting. And then and the black dots indicate the soils, and where we've got bedrock is in the yellow triangles. And so, and again here, there's that contact with the Virginia Formation down this way, and then the St. Louis headwaters. And in particular, in this area, this is where we have the identified titanium oxide deposits. But not only that, there is some exploration going on, looking at potential for nickel and copper also in these areas. And so there is more work being done constantly through these watersheds. Look at chemistry. Okay, so here's some preliminary results. I can show you some. This is just a comparison between the 3 watersheds. This is copper now, so these are the copper concentrations for bedrock and stream sediment samples. Filson Creek here, what you'll notice is the larger the dots and the more reddish color as you go down in the scale, the higher concentrations. And we can see here, we get pretty high concentrations through here. And this is where the Spruce Road deposit, nickel deposit, has been, copper nickel deposit has been identified. And it is pretty much at the surface through these areas. And so you would expect to see these high values. And you can see a lot of higher values even in other portions of the watershed in Filson Creek. And then compared to our Keeley, the concentrations are much lower, which works out with our system, which we thought would occur. If we look at the St. Louis copper concentrations, they're a little high, but not really that much high, not high, compared to what we're seeing in Filson Creek and Watershed. So that's in the bedrock and sediment soils. This is actually in the soil, I'm sorry. That was in stream bed sediment. In the soils, we're seeing something similar. You can see here, again, where we have the deposits near the surface, we're seeing much higher copper concentrations in the soil, in the sea horizon, the lower horizon. Where we get Keeley, they're a little higher in the soils than what we saw in bedrock, but still in the stream bed sediment. But they're still relatively low compared to what we're seeing in Filson, and then really low stuff, what we're seeing in the St. Louis watershed. The nickel. Now, the nickel, we're seeing, Filson Creek, we're seeing higher concentrations in the bedrock and the stream sediments in that same location area. But you can see through the Keeley watershed, we're also seeing relatively higher nickel than we're seeing relative compared to the copper values. And it rolls back to how the minerals are being held in the bedrock and in the soils. The nickel can be associated with mineralization that's within the silicate oxidized bedrock. And that's all this bedrock through here. You can see the purple. There's nickel in all that bedrock. It's just that when you get to the sulfur-bearing minerals and deposits, there's higher nickel. And so you can still see really high values of nickel in the watershed where the deposits are located, but you can also find relatively high concentrations in the areas which don't have the deposits, which you don't see with the copper. The copper is really higher and much more in the areas where you get the deposits. Now, when we compare it to the St. Louis, similar type scenario, where we see actually where some of the basal part of the complex is located, we do see some higher values for nickel. But again, that's associated with the silicate minerals, which are throughout a lot of the bedrock through that area. In the soils, similar type thing, where we see really high concentrations where the deposits are located at the surface, but we also see higher concentrations where they're not. And so, not as high as in the St. Louis watershed, but they're still much higher than, bigger difference than what we see with copper. So that's with the bedrock and the soils now and the streambed sediments. Now with the water quality, we've done some preliminary work with data from 2012 to 2014. We're still waiting to get some of the spring data from this year, and we're still sampling, as I mentioned earlier. But I'll show a quick comparison of what we find for median and the range of concentrations we're seeing for dissolved concentrations in the waters, and looking at temporal changes throughout the watershed between that time period, and then do a comparison between the three watersheds. Just give you an indication of what we're seeing as far as water quality data. I'll let you know we started with a research lab within USGS, and then we actually switched our labs because of they provided more opportunities for doing different types of analysis with the National Water Quality Lab in USGS. And so when we look at the results, there may be changes as far as what our detection limits are, but they don't change a whole lot, but just so when we look at the plots, so you can see. And just to get a general concept of what we're seeing is typically the waters were relatively dilute. They didn't have a lot of dissolved ions in the water. In fact, if you look, these are a comparison with the pH and the specific conductance values. And specific conductance is basically an indication of how much dissolved material might be in the water. And if you look at these values, they typically range between as low as 23 to as high as 105. And looking at, I'm a groundwater hydrologist. I look at groundwater. I look at a lot of surface waters. These are really dilute. They're pretty low. Typically, I've seen, for instance, you mentioned White Bear Lake. I work on White Bear Lake. The conductivities there are about 300, typically. And so these are pretty low. So there's not a lot of dissolved material in the background water concentration. And then the pH values range between 5 and 8.3, what we've been seeing. And so there's a good range. Some of the lower pHs may be associated with mineralization, but it also is maybe associated with bogs and wetlands. Where you have more wetlands and bogs, you typically have lower pHs. And so that water being added into the stream then may decrease it. Yeah.
So what effect would that have on like wild rice beds? Or isn't that that's not your project?
Well, that's not my project, but you know, a lot of the wild rice lakes, I don't think pH is a major factor. Nutrients, I know nutrients are a big control on wild rice population. Also, the stability of waterways. And you know, during different growing stages, the wild rice, they need stable levels as well as they need changing water levels. And so it's all relative to those factors mainly. I'm not sure how much pH is a factor, but I don't believe it's a major factor. Thank you. Yeah? So I'm going to show some things that are called box plots, and I don't know how many people have used box plots before, but just to let you know, this is how they go. And the black line within the orange box here represents what the median value is. Basically, that represented what the middle value is for the range of values we're looking at. And the orange box represents where most of the data is, what we find, between 25% and 75 percentile, basically the main 50% of the data. And then we have these 90% line and 10%. So if you look at it, most of the data is within this area. And then these little red dots will indicate where we have outliers. So if we have something really high, we can identify that. And so I'll be showing these plots over time for each of the watersheds to give you an indication how they're changing over time. The other thing is, one key is water quality will change with how much stream flow. And so the concentrations will also vary often with stream flow. And so I'll be showing you low, on the plots I put down low, medium, high, indicate relatively how much what the conditions were, hydrologic conditions, what the water level, what the flow rates were. And then the red will indicate where we have a detection limit, so we can't detect anything or report anything lower than that. So I'll show you that quickly, some of these plots. Okay, so again, this is the water quality, and this is for all three watersheds combined. And if we look, this is for the amount of calcium, magnesium, sodium, and potassium. So these are our major cations. And what we're finding out is that for the calcium, all the values tend to be below 10 micrograms per liter. And again, I mentioned all these are pretty dilute waters. They're not really high concentrations. But what we do see is a pattern where when we have low flows, we typically have larger ranges of our major cations, and the median values are higher. And so when you have low waters, you get you get higher concentrations of the calcium. But they're still pretty low, tend really low. Magnesium, similar type of situation. Sodium, and why I put sodium down is there isn't a whole lot of variations. It's pretty low. But look at all these red dots. That's actually from one site that's in the Keeley Watershed, our control site, basically, where we're not finding really high concentrations. But we do find high concentrations of sodium at one site. And I think it may be because we're getting some groundwater contribution into that site, where we're getting more sodium. And we also see that with the chloride values also. And then potassium is pretty low. And it varies a little, but not major. Now, one thing I mentioned is our dissolved organic carbon. That's here, representing. And again, there's some variation, not a whole lot, but the main thing is that on average, we're looking at about 25 milligrams per liter. That is really high. In fact, we showed that to an expert in USGS who does a lot of work all across the nation, all across the world with dissolved organic material or VOC or organic carbon. And he said there's some of the highest values he's ever seen. And that's because we got all these wetlands, everything's present, it's pretty obvious, it's going to be there. But I think it's a major factor in understanding that because we have these high VOC concentrations, it also may keep down a lot of the metal concentrations. I'll show some of the results we got with that remodeling. Sulfate, everyone talks about because there's sulfate. What are the background concentrations? They're typically less than 3 milligrams per liter. And it's pretty low. I mean, the standard is 10. And as you see over time, concentrations tend to be lower, and it can be lower during lower flows, but it's variable. But still, I think the overall message here is that we're typically seeing concentrations that are less than 3 milligrams per liter. So now, the metals. What do we see with copper and nickel? Well, with our copper, we're seeing concentrations that are generally less than 10 micrograms per liter. Now, I'm stressing it's micrograms per liter. That is 1,000 times less than milligrams per liter. And so these are really low concentrations. And really no distinct pattern with changes with flow as far as the concentration. Nickel, we're seeing generally less than 8 micrograms per liter. And typically not a strong pattern. Iron and magnesium, we're seeing a larger range and typically a higher medium concentration with the lower flows. And so they kind of react similar to what we're seeing with the calcium magnesium. So when you get lower flows, you get higher concentrations. Okay, so what does this mean relative to where we are seeing where deposits are located in the bedrock geology? Well, if we look at these values, here in Keeley Watershed, this is for copper, dissolved copper. All our copper concentrations are less than 2 micrograms per liter. And so they're pretty low compared to what we're seeing in the Pilsen Creek watershed. And if we look, this diagram is kind of a little bit, but if you look, the stream kind of flows this way through these, comes down, and then discharges out, and then there's this other section that comes through here. But if you look, as we go flow, concentrations between 1 to 2 micrograms per liter. Then it hits where the loose road deposit is exposed at the surface. And you can see they jump up. Now again, these are micrograms per liter, so it's not like a huge change. But they do increase over time. And then when you get the trip coming in, the other trip coming in, between 2.5 to 3, all of a sudden the concentrations go down to 5.9, and then they go up to 9.6. Now, this is for one period, June of 2013. We're seeing very similar results in each of the time steps we're looking at. And so there is an association where we see an increase in the water concentrations where we have higher copper concentrations in the bedrock and the soil. So there is an association. In some of these areas where we have buried deposits, we don't see a big change to this area. Because again, we've got glacial material between the bedrock and the stream. Okay, now comparison quickly I'll do this between the three watersheds. Here's Filson, Keeley, in St. Louis for calcium. We have higher concentration of calcium in the St. Louis and higher magnesium concentrations, and also with St. Louis potassium. These are our major ions. That's because we've got more glacial material. I think that's where we get more of the calcium and magnesium. The concentrations aren't very high at all, but they are higher than compared to Filson and Keeley. When we look at Keeley, here's that sodium. We've got this huge change between Keeley, Filson, and St. Louis. Again, it's one location that we're seeing this huge change. And I think we're seeing that may be due to groundwater coming in. Okay, our organic carbon, pretty similar for the ranges. Sulfate, they're a little higher actually in the St. Louis River than what we with Filson, where we have some of the copper on the surface. But they're still pretty low. And then our dissolved metals, Filson, we have higher copper versus Keeley, St. Louis River, so that's making sense. It's also with nickel. Even though the nickel can be found throughout the watersheds, you still have higher concentrations where the deposits have been identified. So we did see higher concentrations there. And then iron and magnesium, pretty similar, although the St. Louis is a little higher. Okay, so the other thing I talked about, our third component of our program is doing some conceptual models for the hydrology. And so what we're doing is we've determined water balance for each of the watersheds. Determined from looking at stream flow records and other information, we've got a water balance for each of the watersheds that helps us. And then we've created what are called synthetic hydrographs throughout the watershed, and that helps us with our water quality analysis. And these components have been added and are helping us with doing some water quality modeling. And really, what our focus is with the water quality model is to kind of establish what are the important parameters from the water quality and the hydrology that are kind of going to be controlling the metal transport at various locations, or how the metals may be moving. And so we're doing that by looking at a couple of different software packages. The USGS Otis transport model, so that tells how metals may be moving downstream. But then we also working with that with what's called a visual MinTech, which is an equilibrium model, which tells us what the chemistry is at each of the sites. That's what we're trying to simulate. And to get a better handle on this is kind of work that we're doing right now, so we're still coming up with results, but we're also going to be doing a tracer test at Filson Creek, because that's where we're seeing most of the changes in the water quality, particularly the copper. And that'll help us with some of the transport model. So we're working with a lot of researchers, as well as the Forest Service and people outside the USGS on that. And then finally, let's see. We also have research in the USGS, Bob Seal and the Tech that are doing some bioluminescent modeling, which is basically a risk assessment type of value that's going to evaluate that's really looking at the effect of the dissolved organic material or dissolved organic carbon in the watersheds on, and looking at cations and various metal species and how that will change. And what they're seeing is that, like I said, it's a really complex plot, but basically what they're saying is that if they include just the major ions, that there might be some risks, toxic effects of some of the species in the watershed. But once you take into account the amount of dissolved organic material, there's very few locations with the current watershed that would really affect any aquatic species. Now, that's just with the natural conditions as it exists now. So it's just to get a handle on that. We've done that model.
Excuse me,
Yep.
when you're saying, your biotic species, are you talking invertebrates? Are you talking fish? Are you talking plants?
Yeah, a lot of this is looked at just concentration. So really what you got to look at, they look at a variety of the species, and so it's not really species, it's more relative to the concentrations. And so I'm not the expert with this at all, but when they do the toxicity test, they're really kind of looking at the main species that EPA looks at for the toxicity test.
So fish and bugs?
Yeah, a lot of fish and bugs. So it's not my specialty. So finally, usually you say, hey, does anyone have any questions? I got a question for you. I'm throwing this back at you. There's various parts when I walked along the creek, and I find this stuff that, it almost looks like stuff that's precipitated out. Come out of the water, and goes onto the plants, goes onto the rocks. You see the white stuff that comes on here? And I think it's where we get groundwater coming from. Because I see a lot of tamaracks and a lot of species that kind of indicated potential groundwater coming in. But I see this, and I'm just curious. I don't know what it is. And I've talked to a lot of people, and they think it might be a precipitate. I thought instantly, oh, this is some type of precipitate. But there's not much dissolved material in the water. And so, I don't know, it almost looks like a aluminum oxide to me, or it could be like salt. But they said there's no way. And so, I throw that out at you, and maybe you have some ideas.
Well, so it's not carbonate.
I don't think so.
You can test for that. I mean, like this lake has carbonate or something.
Yeah.
But you could test for that pretty dark.
Oh yeah, I know.
Yeah.
Good.
Yeah.
And I'm going out to collect some. It was a surprise to me when we were first out there, and I didn't have anything really to do with decent sample collection. So I'm going out there again and doing a better job. But if anyone has any ideas, I really would appreciate it. But if you have any questions, time's now too.
So you did have a copper nickel mine there. You remove some of the wetlands and dig a pit and have groundwater flowing into the pit and possibly flowing out of the pit. Plus you're going to have waste rock piles exposed to rain and runoff. Any idea what the addition of that to the system, what the impacts might be?
Well, it's highly variable depending on what the mine design is, where they do it, how many wetlands they take out, what the chemistry is. It just depends on a lot of different variables that really need to be assessed once you've got a plan as far as how the mine would be designed. In these locations, this isn't where polymet's not involved in any of these watersheds, so there really isn't any mine designs at this point to really properly evaluate that. And so this really just kind of establish a baseline characterization that we can work with. And I think what you have to do is look at the mine design. Is it surface? Is it underground? Where are they processing the ores? And then how's the tailings or what they're going to do with that afterwards. There are a lot of different variables that, in a study like this where there isn't even a proposal, you can't really evaluate at this point. I think those are things, what we're hoping to do is get at least the baseline established, and then looking at potentially what we hope to do with the water quality models is try to evaluate if we increase the concentrations of, let's say, metals or copper or nickel and things, how does the system react to that increase? I think that's the best way we could do with our work to evaluate that.
Is anybody doing a study in the Polymet area where you do have mine proposals?
Well, they've been doing a lot of work. A lot of people, companies and environmental companies and such have been doing a lot of work up there. We haven't been involved with the Polymet at all. Yeah. Any other questions? I hope it was clear. Okay, good.
It was great. Harry, thank you very
Thank
much.
you.
I think we all appreciate your presentation today.